visiting your grandpa or something. Right? He's like mumbling to himself. If I just can get this thing to work, if you come here, Sonny, help me out now, Aiden. Good morning, everybody. Welcome to class. The local time is 9:45. No, 9:49. 9:49, and we will begin our program on igneous rocks at the top of the hour. That's a little more than 10 minutes from now. So let's settle in, say hi to a couple people. Got a couple gifts I need to acknowledge, even though I said I wasn't doing that, but these are gifts tied to the class. And I'll stay out of your way, and I'll stay out of the students' way as well, so you can copy down the outline. Are we functional? Where are you viewing from this morning on this sunny, windy, supposed to be 50 degrees today. It feels like spring here. Feels wrong, but I'm not going to complain. The sun is great. Haven't seen the sun in quite some time. Hey, Sherry and Bob from New Glarus, Wisconsin. Hello. Great to see you guys. Relatives of mine. England, Minneapolis, Santa Cruz, California, Vashon Island, going very quickly now. Geologically speaking, Spain, Denver, Whidbey Island. I'm just grabbing place names. I can't quite get your first names as well. Germany, Thomas is in Germany. Sharon's in Missouri. Portugal, good morning. Knoxville, Tennessee. Another Portugal, Andre, or the same one? Doesn't matter. I'm glad you're here. Bo is from Copenhagen, Denmark. Los Angeles, California, Lacau, Finland, Marion, Virginia. Good morning, Jack. Northern Norway. Anna Olin, Northern Norway. Wow. How much daylight do you have now? I'm not going to complain about the sun. If you've barely seen the sun between 10 a.m. and 2 in the afternoon, or even less than that, I don't know. What do I know? Knoxville, Tennessee, Visalia, California, Nephi, Utah, Brisbane, Australia. That's Peter. Andre is in Germany. Hello from India. Hello. Bavaria, Germany. Columbia Gorge, Toronto, Forest Lakes, Arizona, Ooswil, Switzerland. Pocatello, hey, Uncle Phil, another relative, Phil Jose, checking in from Pocatello. Screen's dirty. Let's do a couple more. Oh boy, I can't keep this crowd quiet this morning. This is just like too much. There's like 4 people here. We'll see how many we get in the next 9 minutes, but it's a Friday right after a quiz, so we know how this goes. But I'm glad you're here. We got almost 500 already. 500 there, 4 here. 5. Zealandia. Rainier, Oregon. Wander, whatever, is from Armandale, Australia. Hello. Charles says hello. What's on the tray behind me? Oh, I guess you'll have to wait and see now, won't we? Won't you? I love you too, Deborah. Okay. Post Falls, Idaho. We got a lot of spuds here this morning. Bob and Kathy from Coopville. Good morning. Okay. So I mentioned last show, we're not doing all sorts of gifts and taking time to thank for gifts. That was kind of part of building community back when I was home with the cat and everything else. Good morning, Hope. It doesn't feel right to do that here. However, people, of course, are sending things to the school. And so I guess I will share things if they're tied to the school, especially the class, especially if there's a treat for the people. So this arrived yesterday, and I did not see a name. I'm sorry. This is a very, I've never seen something like this. This is a very, what appears to be a very expensive, unique gift. Sheepskin chamois or chamois, or how, I don't even know how to pronounce it, let alone really understand it. But this is, I guess, sheepskin or synthesized, whatever. I don't know, but I really do. So thank you, anonymous person. I'm guessing, since I didn't see a note, I'm guessing you want me to use it on this, but I almost don't want to. Like this is so, I almost want to use this on like camera lenses and computer screens and things like that for the class. So maybe I'll hear from you and you say, no, I gave you that thing to use on the chalkboard. That's why I gave you, and if you insist, then I'll do it that way. But otherwise, I don't know. I don't want to mess it up. I don't have nice things. When I get something nice, I don't really want to use it. I want to put it in like a glass case. JC. And oh, they're rolling in now. We got Eve and we got Tawny. Oh, they're hugging. Not really, but close to it. Classmates. So thank you, anonymous chamois person. And you guys' ears need to perk up for this one. So this arrived. I got an email from the CERC desk, information desk, and they said a gift has arrived for you. I didn't even know people could mail stuff directly to the information desk in the CERC. So I went over there and, can I help you, sir? I'm like, yeah, I think there's like a gift for me. And they're like, I don't think so. What? Who are you? I'm like, you don't know who I am? No. So we went back and forth. They finally figured it out. They found this box in the back room. And here's the note. Many thanks, Professor Nick and class, for sharing your 101 class with us townies from the Andersons, aka Mount Sylvania. And so these are 24 Ferrero Rocher hazelnut milk chocolate Valentine's Day candy gift box. So it's Valentine's Day early for you. And I don't know. We'll see how many show up today. If we don't have, well, you're going to have at least one of these, maybe two. You want them now or you want them later? I'm going to bring them to you now, okay? And it's your choice, okay? You can nibble mid-lecture if you like, but there's 3 of these. And thank you, Andersons, for your generosity. Feeding the chickens. All right. Oh, you missed the whole thing. You missed the whole thing. So help yourself, please. All right. That's very kind of you. The students did very well in the quiz. So I can't be too upset that we have half the class showing up today because they stepped it up. I came in last night to play with the second camera and I had things working, but there was a weird kind of delay thing that I haven't figured out. So I'm still going one camera this morning. Tim, good morning. I have autofocus on and you'll see why in a bit, but I want to hold up a bunch of samples today. We are talking about igneous rocks. And so we'll see how that works. And if I do a bunch more kind of hand samples showing, then I'll keep that autofocus on. But if it keeps, is it the phrase hunting? If it keeps hunting for focus and it's a bit of a distraction, then maybe I won't have it on again. But I'm trying that. That's my new wrinkle this morning. MOVA Globes, the corporation itself, left a comment on one of the YouTube lectures. So somebody tipped them off that I'm showing this. So they said, nice globe. And I said, send me one for free. No, I didn't. So I went to their website and it's not magnetic field, it's light generated. I don't really even know more than that, but I think that's what their website said. Okay, I got 2 minutes. Let's see if I can't get something going in the room here. Pretty quiet this morning. But I'm glad that you're here, and thank you for joining us. That's right, Emily, too. Because you took the initiative, please take 3. Absolutely. Come on, you all did really well on that quiz. Now treat yourself. This is from the Andersons. Oh, we need a macho something.
For once, my nails are not sharp enough.
Oh, yeah, my nails.
Yeah, this is.
Oh, this looks expensive. What are these?
They're really good.
You've had them before?
Oh yeah, no. Every Valentine's Day, my mom gives me like a ton of them.
She does?
She knows they're my favorite.
Oh, well, this is exciting.
So they're like.
Oh, I can smell them like they came out of the Willy Wonka factory. Oh yeah, Jordan, take 2. Mason's not here. Take.
Oh, he's coming.
What?
I've seen him on the way here.
Oh boy. Oh boy. Oh, he's getting coffee for everybody, and now he's going to throw the coffee across the room.
My favorite candy in the world.
Casey, do you really know? You guys have expensive taste. I've never had one of these things.
Really?
Yeah.
Dude, Ferrero Rocher is like one of the best.
How do you say it?
Ferrero Rocher.
My God. I just go home and eat handfuls of dirt. I don't deserve stuff like this. Oh my God, it's 10 o'clock. I got to get started. I can't get this up. All right. Well, the rumor is Mason's on the way. Well, good morning, everybody. Hey, now, it's Friday morning. It's the morning after a quiz. People did well on the quiz. I'm encouraged. Almost everybody did very well. And so whatever you were doing, I don't know if your drill sergeant Mason did it or I don't know what it is. Let's take ownership. You did it, but whatever you did, keep doing it. Tawny wants to say something.
I just have a question about it because I went to the entropy and I thought that I only missed like one question.
Yeah.
But then I got down even more points than what I thought. Is there any way to see what we got wrong?
Sure. Yeah.
Okay.
Yeah. Okay. So good job. I'm encouraged. Hopefully you're encouraged. Keep at it. But let's not rest on our laurels. Let's make this happen. Now, Jordan, you got the phone out. Not only you, unless you're taking video of me, which I totally endorse. Not really. Let's put the heroin. How about we take the heroin and actually put it like in the backpack? Get it like off your table. It's heroin. It's addictive. This phone thing, and I'm trying not to comment on it every time, but like the wrist is ready to go, the veins are popping, and you're ready to just keep hitting. We can do better than that. Pedro's here, for goodness sake. Pedro, did you watch the live stream in your apartment and you saw there was chocolate and you're like, I got to get in on that? That sounds, no, you were coming anyway. Nice. Okay, good. Okay, enough preliminaries. We're locked in. We have a decent sized group now. Let's do it. You've got the outline. The discussion is igneous rocks, but this is really a 2-day lecture. This is a lecture that's going to get us to volcanoes, and everybody loves a good volcano. And I have video footage for you this morning, right off the bat. But we're going to lock in the best that we can with this. So my opener, are you ready? My opener is this. Are all volcanoes the same? The answer is no. Some volcanoes erupt violently, and we are very afraid of the next volcanic eruption in certain places. There's other volcanoes that erupt rather passively, and you can go right up to that volcano as it's erupting and sit down right on the volcano and have a little bag of Skittles and some fancy chocolates and watch the eruption and not ever be in real danger about the whole volcano blowing up. We're still trying to settle down here. I know you're distracted by the chocolate. What is the reason we have such different kinds of volcanoes? Why are there different kinds of volcanoes? Is there a pattern globally? to where the quote-unquote safe volcanoes are compared to the quote-unquote hellacious volcanoes are? The answer is yes. And my motivation is to get us to care about chemistry this morning. Boy, wow, really? Yes. There's a chemistry answer to why volcanoes erupt differently. And so that's a warning. As you see on the outline, we're going to go to silica tetrahedron. Silica melts. We'll do it just briefly. I don't want to dismantle all the nice energy we have right now, but that's where we're going. We're starting sexy. We're getting down to the chemistry in a magma, and then we're coming back and looking at igneous rock samples before we quit. And we end where we end today. We'll just go right into it on Monday morning when I see you next. This is a 2-day lecture that will be to be continued on Monday. Okay, there it is. That was the introduction. It's done. All right, let's go to some video right off the bat. You've got the outline. It's going away. It's not coming back. Not coming back. Can I get us back to thinking about what we were doing late yesterday? That's the first thought. Can I get you back to that? Give me a second to get myself organized. And I'm going to do a fair amount of this, so I want to just make sure the cameras are just set as well as I possibly can for you and for the home audience. That's us. We don't want that, meaning the live stream. But I found some video that I was pleased with this morning, and I ripped it off of the internet, and it's from the USGS YouTube page. All right, so I think, give me just another, not bad, this will work. You've got a nice shot here in the classroom, and you're the paying customers. We care more about you than the guys at home. I shouldn't have said that, but I think I did. So this is what the volcanoes look like in Hawaii. Hawaiian hotspot, making one of these volcanoes at a time. We haven't named it yet. We haven't learned the kind of volcanic style. We just know that it exists. It looks like this. Now, this is a very different kind of a volcano. This is Yellowstone in Wyoming, another hotspot. But as we discussed late yesterday, we're melting continental crust as opposed to ocean crust. So there's your first tip. We have different volcanic styles because we're either melting ocean crust or we're melting continental crust. It's apples and oranges, really, as far as chemistry is concerned. Just trying to get you interested. Now, you saw this yesterday. We're looking at it again. There's that Hawaiian hotspot. And look what the artist, the animator, has done for us. Taken this relatively thin oceanic crust, melting it, and we're getting these Hawaiian-like volcanoes. That's all we'll call them right now. And now here, you'll also, I'm reminding you, we saw this late yesterday, and notice that this is a totally different scene. We have magma chambers. Those orange things are rooms underground that we call magma chambers. A chamber's a room, right? So we got these magma chambers. But the key question this morning is, what is the chemistry of that magma? I guess if there's different kinds of volcanoes, there's different chemistries of magmas. So not all magma chambers are the same. What the hell is going on right here? Sorry, Patrick. What the hell is going on right here? This isn't what we saw in Hawaii. Where's the orange stuff? It's orange underground, according to the animator, but I don't see any orange lava coming over the surface. So we've got some things to discuss this morning. Now, forget the animations. Let's go to some actual real footage. This is real footage from, back when I used to take students from this school over to the Big Island of Hawaii. We used to do field trips. At the end of the fall quarter and before Christmas, we'd spend 10 days over there, camping and hiking and going to see this. I didn't shoot this footage. This is from a private video company. But my point is, this is Hawaii, and this is how fluid, this is how runny this lava in Hawaii can get. And we just don't have this experience in Yellowstone on a massive scale. On a minor scale, we do, but on a massive scale, look at this stuff. This isn't slow motion. This is almost 30-year-old footage. And we got the zoom lens cranked, baby. I mean, what is this liquid? Is this solid? Is this like both? Like, what actually physically is this? Oh my God, now we're actually going to walk out there? Yes, if you're a geologist that works for the Hawaii Volcanoes Observatory, funded by the USGS, the U.S. Geological Survey. Some people from this class now work for that outfit. Angie Diefenbach is one student who used to be in this room, and now she's working and is a volcano expert and flies drones and goes out. I mean, this is an accessible, tangible job for you if you want to continue in this. But you're like, I don't know, why the hell would I do that? Look at they got masks before the pandemic. What are they doing out there? Well, it's not exactly, yeah, look at that car. Carl out there, like, okay, I'm going to go get a sample. Watch this. I'm going to go get a sample. Carl, go. Carl. Attaboy. Go, 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 go. Go, run. Carl. Like, what year is this? I'm just like, that's about as close as we can get to directly sampling magma. I mean, we're still pretty crude. Now, this is what I found this morning. Kilauea erupted pretty spectacularly about 2.5 years ago, you might recall, in the spring of 2018. Some of you are nodding your head. Pedro remembers this. So there's lots of great footage for free you can get to on the USGS, or maybe you have other sources as well. But I want you also just to notice it's orange. We don't have gray ash everywhere. We don't have a huge explosion. Instead, we have this incredibly fluid magma. I'm getting impatient. I want to go to the other one. Look at this. This is real time. And it's kind of fuzzy because there's so much heat coming off of this river of lava that there's this very real shimmer. Has anybody been out to the active lava in Hawaii? Probably not. It's quite an experience. I mean, you feel completely alive when you're out there. Now, we weren't as ballsy as this guy, and he's going right up to the edge of this river of lava. Again, this is not manipulated, this is real footage. But these rivers of lava were like clocked up to 20 miles an hour. Like you can't even outrun this lava. Like it's surprising how fluid this stuff is. And I'll shut up for a second because I think there's a little bit closer footage that's quite spectacular. But if you want to watch a bunch more of this, it's mesmerizing, number one. You lose hours watching all this stuff. Or better yet, if you're there in person, you just sit there like with your mouth open, like eating some Skittles and just watching this. And, we used to go out in the middle of the night. So we have headlamps and walk, for a couple of hours to get out to the active flow. And then it was like, which planet are we on? Pedro. This flows into the Pacific Ocean. So this is a vent that opened up, I think it's vent number 8, that opened up right in the middle of a subdivision. So there's other footage here where they pull back and you can see, the mailboxes in the little subdivision and the little circular driveways and the whole thing, So it's like this fissure had opened up in somebody's backyard. And then, yes, this stuff is flowing from the vent to the ocean, which is just a couple miles away. And then it dumps into the ocean and it solidifies very quickly in the ocean and becomes an igneous rock we're going to talk about. Yeah, look at that. This is great stuff. Again, it looks like it's slow motion, but it's not. If you look carefully at the guy, he's real time. And, it's restricted to go this close for obvious reasons, but it's an amazing scene, and I highly recommend it if you get a chance. And it's erupting right now, although it's not as accessible as it once was. Anybody else want to ask anything just about the Hawaiian lava experience or anything related to that? Mason?
This is more of a comment, but you can actually go on helicopter tours.
Sure.
It's really cool.
Yeah. So Mason's done the helicopter thing over the top. Yeah, there's private companies that do that, and lots of experiences. Wonderful. Okay, so I've tried to set the hook. Oh, no, let me do more. So here's a volcano on planet Earth. It's in our state. It's Mount St. Helens. Now let's watch it erupt. We don't have any video. We have 0 video from those first few seconds in May 18th, Sunday morning. And these are a bunch of still photos that have been stitched together to give you the sense of what it looked like. But I don't see any orange, do you? I mean, this is a volcano on planet Earth, but I don't see any rivers of orange. Instead, I see nothing but gray ash, and I see a whole portion of the mountain failing and blowing away. and slumping to the north. We'll devote 2 lectures to the Cascade volcanoes coming. But the point is, this is a totally different experience. Why? This one had a magma chamber. Why didn't those magmas come out runny, just like we saw in Hawaii? Or a shot inside of the crater. Have I shown you this already? I forget. Maybe early on in the class, I forget. This is, again, still photos all stitched together, taken by a webcam inside of the crater in the mid-2000s. So you might actually have a memory of Mount St. Helens being active for just a couple of years, through 3-4 years, I think between 2004 and 2008. And again, no orange, no runny stuff. This magma looks stiffer. This liquid is coming out. It's erupting. This is lava that you're seeing there in the steam, but it's not this river of fluid material. And then we go back to the Yellowstone hotspot thing, and what are they doing here? What the hell are they doing? That's a volcano? In southern Idaho? That's what it looks like when the Yellowstone hotspot does its thing? It makes this incredible kaboom like the size of, and leaving these huge craters? Yes. So we are tackling today and next time why we have such violently different magmas. Okay, you're all in now. I can feel it. You're all in. This is what a silica tetrahedra looks like. It's on your outline. Silicon, oxygen, tetrahedron. So we're trying to answer that now for the next few minutes. We're going down to the microscopic level inside of magmas around the world, inside of lavas, if you like. And now this is chemistry, of course. This is a silica tetrahedron. So the red thing in the middle is an atom of silicon. You know silicon from our absolute age date. That's an element, silicon, S-I-L-I-C-O-N. And the most stable configuration of combining silicon with oxygen is to take 4 oxygens and surround 1 silicon. So what you're looking at is this cute little pyramid. This cute little pyramid that's called a silicon-oxygen tetrahedron. Tetra means 4, right? So the most stable way at the microscopic level is to have 4 oxygens surround 1 silicon in this particular configuration. Slang, we call it a silica tetrahedron, because if you recall, silica, which we've talked about, remember we talked about crust having more silica than mantle? That's what we're talking about again. We don't say silicon oxygen each time, we just say silica. So this fundamental building block inside of a magma, all magmas, Hawaii, Yellowstone, St. Helens, I don't care, we want to visualize these guys at the tiniest, most microscopic levels. And that's because this is a pie chart of planet Earth. You can read these. The red is almost half of planet Earth. If we ground up our planet and analyzed it elementally, chemically, almost half of our planet is oxygen, and more than a quarter of our planet is silicon. So there we go. We're going to have silica in every magma. Every lava, every igneous rock has silica, lots of silica in it. And you can see that there's other little slivers of the pie. So we have other elements that also make up our planet, of course. But it's really this silica that we're zeroing in on. Now, this is going to put us to sleep, so I don't want us to put us to sleep. So what I want to do instead is use the rack that I have here, the cart that I wheeled in from the lab, and try to keep this going the best I can. Now, you've all had the minerals identification lab this week, right? And you're going to be tested on that minerals quiz next week. Give me a second. I'm going to position these cameras so that I can hold things up for those guys at home and you guys as well, and maybe have everything in focus. We'll see if this works. So, of course, mistake to show that first. If you look carefully in this model, so this is from the minerals room. We have a mineralogy lab right next door. Tim is nodding furiously because he's sitting in on mineralogy. Okay, so this is a way to look at the chemistry inside of a magma or in a particular mineral. So notice that the black guys here are, every black is surrounded by 4 reds. So each of these little guys is a silica tetrahedron, hooked onto another silica tetrahedra, hooked onto another one. You can see it now. So it's really a question of how are these tetrahedra arranged at the microscopic level to eventually form minerals. Okay, let me try to make this applicable to what you've seen in the lab this week. Audience participation time. What's the name of this mineral? This is quartz, thank you. This is quartz. This is a crystal of quartz. It's beautiful. Everyone loves quartz crystals. It's a mineral. It's made out of silica and oxygen. In other words, there are tinker toys, or these silica tetrahedra, linking up at the microscopic level inside of this quartz. Let me show you another set of quartz crystals. How close can I get? The focus is remaining pretty good for the home viewers. I would not say it's the same for you, but maybe you can see well enough from where you're sitting. That's not bad. We'll make this work. So there's more quartz crystals here in a geode or an agate. It's a mineral. I'm asking you now, does quartz have cleavage, yes or no? Does quartz have cleavage, yes or no? This is from lab this week. What do you got? Quartz never has cleavage. Hope you're on it. Quartz never has cleavage. So here is rose quartz. I don't think you saw rose quartz. Somebody sent me some rose quartz. That's how I roll. I get boxes of rose quartz. Whoa, what I got? What is this, chocolate? No, it's rose quartz, dog. Okay, great. So this is quartz that is pinkish, and I want you to notice that it sparkles light, but it doesn't sparkle light all at the same time. And the point is that you remember cleavage planes. Remember this now? You can identify certain kinds of minerals by looking for cleavage planes on the minerals. Here's a pink mineral that does have cleavage. You can see the light reflecting all at once, like a mirror reflects light. You remember this now? Oh, yeah. Morgan wants to. Whoa. Morgan. Why'd you say? I didn't say Morgan. Did you? Did I? I said Morgan. I'm sorry. It's Mason. It's potassium feldspar. Mason's in show-off form right now. That's good. He's got it on the tip of his tongue. And this is potassium feldspar, and yet this is rose quartz. They're both pinkish, but it's the potassium feldspar that has cleavage planes. I'm flashing you. I'm flashing you. And this is rose quartz that is also shiny but does not have reflections of light all at the same time. If you didn't understand cleavage from across the lab, maybe that helped. What am I doing here? I'm saying that quartz never has cleavage because the tetrahedra are randomly arranged. Let's jot this down. Quartz is an independent silicate. The mineral quartz is an independent silicate. I'll break it down, but I just want to do it verbally for you. One more time. Quartz, the mineral quartz, all kinds of quartz, amethyst, rose quartz, milky quartz, smoky quartz, I don't care. It's an independent silicate, which means it's a silicate mineral. It's got a ton of tinker toys inside of it. If it's a silicate mineral, that means it has a lot of silica in it. But an independent silicate, well, now he's dropping stuff. An independent silicate, okay, it's clown show time now. I got too much going on. The tetrahedra are there, but they are not organized. An independent silicate mineral like quartz has the tinker toys, has the pyramids, but they're not joined in any particular way. And if your question is why, I don't know the answer. I don't know the answer. But quartz does not have cleavage because of this tetrahedra business not getting their act together. However, just generally, this doesn't show tetrahedra necessarily, but I grabbed this one just to show that there are plenty of minerals that have their act together. Their tetrahedra are linked up in very particular ways. So that was a mistake to grab that one. But thankfully, I have this. This is a similar look at tetrahedra, but this is a sheet silicate. A sheet silicate, where the tetrahedra are actually lined up in beautiful, perfect planes. Tim's begging to say this one, and I wish you would. What's a very common mineral that is a sheet silicate? Muscovite or biotite. Do you remember biotite? Biotite mica, right? Do you remember what it looked like? Thankfully, I brought some in. He goes back to screwing with the cameras again. Daddy's learning. Daddy's learning. So from lab this week, you remember this guy. These little flakes. These little fragile flakes. These are minerals, and they are minerals that have one perfect cleavage plane. Oh, why not? Let's destroy one. You hear that? It's like I'm tearing pieces of paper or tape apart from each other, and I'm breaking audibly the chemical bonds between these cleavage planes. And what I'm really breaking are the bonds between individual pyramids. So in case you're waiting for it, biotite mica is a sheet silicate mineral. Quartz is an independent silicate mineral. If you have a good memory, when we talked about absolute age dating, I said sometimes you can find biotite, which again are these little fragile guys, in books. So I found a book of biotite. I can't remember if I showed it to you. So there's just thousands of these little flexible guys all packed together where they grew. And there's even a greenish version called chlorite. This is kind of beautiful. There's even some little garnet, looks like there's some garnets in here. Is that autofocus working for the group at home? I can't really tell. Maybe it is. Okay. Questions? We're kind of down in the weeds right now. I don't want to stay here much longer. But I'm trying to give you the sense that those minerals that you saw across the hall have different cleavage properties. Potassium feldspar, cleavage, yes or no? If it has cleavage, it does, then its tetrahedra are arranged at 90 degrees. That's the whole point of this whole thing. Okay, so let's pick up the pace and get back to our volcano discussion. Somehow I'm going to use this discussion of silica in a magma batch, ultimately explaining why we're afraid of some volcanoes and not as afraid of other volcanoes. That's where we're going. Okay, you're still with us. That's good. I don't think I want you to do this right now. And if you do this, you'll be using it on Monday. So this is where we are headed on Monday. If you want to just get something quickly in the corner or something, that's fine. But we're going to eventually get to 3 magma chambers and do some drawing of 3 different kinds of volcanoes. And I'll say it right now, in case you don't see where we're going. Our 3 different kinds of volcanoes worldwide are going to be dependent on how much silica is in the magma. How many of those little tinker toys, how many of those little pyramids are in the magma? That's the ultimate goal. So we're not doing it in this form today, although I'm setting you up for that. Instead, it's time to do some stuff on the chalkboard and not trip over the rock samples and not trip over the laptop and find a chalkboard. God, I'm sweating. TMI. All right, give yourself some room. Let's a little herky-jerky this morning, but I'm finally to where I want to be with you. And the energy is very good, especially for a Friday morning. Lots of room on all sides. In the middle, would you please do this? I want you, if you wouldn't mind, just write this phrase 3 times, almost like you're in trouble. Write it 100 times on the chalkboard as punishment. No, of course not. But now that we know that magma chambers around the world host magmas, rooms underground hosting this kind of slushy material, this liquid rock, this magma, a more descriptive term for the magma is silicate melts, because we know now that silicate melts are going to crystallize into silicate minerals, and we know that silica, the silicon and the oxygen in the apparatus here, is the main thing that we're focusing on. Okay, so for this discussion, I would like to play with the amount of silica in the magma. So in this first one, let's put 45% silica in this first batch of magma, this first batch of silicate melt. And in the second batch and in the third batch, 45, 60, and 75. All we're doing is playing with the amount of silica in that magma. Let me tell you a quick story that might be memorable. I'm an older person now, but I used to be in high school, and I was an athlete in the fall and in the winter, but in the spring, me and my buddies, guys and gals, none of us were in sports. And so school's out at 3 o'clock, and it's, we're about an hour outside of Milwaukee, Wisconsin, and my buddy Guy has a broken down station wagon. We're all going to pile in his station wagon. We're going to drive into Milwaukee every week, like on a Tuesday afternoon, 3 o'clock. Why would we do that? It's like mid-March, the snow's still around, That was a thing. Like teenagers from across southern Wisconsin are driving into downtown Milwaukee at 4 o'clock on a Tuesday afternoon in April. Why? We'd go to the Miller Brewing Company. Well, it's like 1979. Why would we do that? Well, we take a tour. Take a tour of the Miller Brewing Company. About a half an hour tour. Why would we do that? This is a simpler time. They gave you a big old beer at the end of the tour. 16 years old. Here you go, buddy. I did the same thing when I was your age. And then you pound it, and then you take the tour again, and then you drink another beer. And you keep taking the tour. And then you drive home. It was a simpler time, okay? No seatbelts, I don't know how we survived. I'm not proud of the story. However, I'm sharing the story with you because I remember to this day those rooms on that tour, these freestanding copper kettles in these big warehouse rooms where they're actually working up batches of beer. And back at the time, there wasn't all these specialty craft beers. It's like Miller, High Life, and Miller Lite, and that's about it. But the point is, they're kind of whipping up different batches of beer with different ingredients, and that's what we're going to do here. We're going to make 3 different batches of beer, like in the Miller Brewing Company. And these copper kettles, the magma chambers, are analogous to these big copper kettles. So we're putting our copper kettles in the subsurface. You're with me. Okay. So we have different amounts of, hops, yeast, whatever the hell goes into beer. That's how much I know, okay? But in this is silica, right? Silica composition, the amount of tinker toys that we're putting in. Okay, there's a 1-to-1 correlation between viscosity and silica content. Who can help us with viscosity? Have you heard that word before? I'll write it. Somebody, viscosity, Hope? Yeah. Beautifully done. Wow. Hope on fire this morning. Kind of talking about how fluid a lava is, or a liquid. You said liquid. Sorry, you didn't say lava. So I've got a phrase that I like. It's very similar to what Hope was saying. I think of viscosity as a resistance to flow. You have a substance, and what is its resistance to flow? That's describing the viscosity of the material. So Hope even gave us examples, which I appreciate. If I have a pitcher of beer and a pitcher of honey, there's going to be a different viscosity. One is going to be more resistant to flow than the other. The honey is going to have more resistance to flow. Resistance means it doesn't want to, right? So honey has a high viscosity. High viscosity, lots of resistance to flow, doesn't want to flow. Honey has a high viscosity compared to beer or water or iced tea. We have it? Important question. How does silica content relate to viscosity? What's your hunch? Pedro?
Would it be that the more it has, how fast it would be, I guess?
Yeah. Casey?
The higher the silicate content, the higher the viscosity.
Is that what you were saying?
Yeah, I kind of messed it up here.
That's okay. Okay.
In the crust, there's a lot more silica than there is in the mantle.
I'm gonna hold you off there, but Casey's on it for the main thought, and we want that. And here it is. There's a 1-to-1 correlation between silica content and viscosity, meaning, in Casey's words, the more silica you have in a magma, the more viscosity it will possess. Let's get this down. Do I need to write it for you? Let's do it. I'll write it for you, and then we will try to think of why this is. So this is low silica. 40. These are real numbers, by the way. You can go to around the world and visit volcanoes or even igneous rocks that we're going to get to before we quit today, and you won't find an igneous rock with lower than 45% silica. You won't find an igneous rock on this planet that's higher than 75. And these numbers, there's kind of a range in between. So I'm just picking 60 as kind of a kind of intermediate value for discussion purposes. But we can have a magma on planet Earth with 47% or 63%. You get it. There's a range. Rock bottom value, no pun intended, is 45%. Highest on the planet is 75. So low silica means low viscosity. High silica means high viscosity. And I don't know, medium viscosity. What does this mean again? The lower the viscosity means the runnier it is. The higher the viscosity means the stickier that it is, the more resistant it is. And I don't want to screw around much more. Let me just go to it. The reason we have this 1-to-1 correlation between silica content viscosity is really thinking about the chemical bonding between these tetrahedra. If we have more and more tetrahedra in the batch of beer, you know what I'm saying, we're going to have more and more spider webs connecting this stuff together. Does that make sense to you? If we have more pyramids inside of the magma, we're going to have more bonding, more structure, more sheet silicates, etc., and we'll have less and less ability to flow. But the less pyramids we have, the lower the volume of this material. Wrong way to say it. You get it. You get it. Okay? Are you impatient? I would be today. Feels like we could go through this faster. I'm just trying to... I'm building for Monday, more or less, but I'm glad that we're covering some good stuff today, but I'm really building towards a discussion of volcanoes on Monday. I hope that you can see the payoff. I'm looking at the clock. I've got about 10 minutes left-ish. Let's all look together. Oh, yeah. Whoa. There's like there's like black things, and then there's this red line that's like going around. What is that? What is that? Tony, you like that? Those aren't flat. That's not digital. I don't, is that like a sundial? Is that what they call a sundial?
So young that we don't know how to read analog.
Analog. That's what that is. What is this? What the old people look at?
1037.
1037. Is that like the black? Is that did the black arms move then? All right. Okay.
The mnemonic for it, Nick. The more viscous, the less liquid.
Oh, Morgan. What is wrong with me? I'm serious. I actually said Morgan again. I got problems this morning. Okay. We're doing this. There's a global, let's pick it up. There's a global pattern to where we find these three kinds of magmas. It's not random. There is a global pattern. Let's not do any more screwing around. If we melt pure oceanic crust with, I don't know, a hot spot in the middle of the, Pacific Ocean, and we generate magma out in that pure oceanic setting, we will create low silica magma, and we will call that magma, Mafic. I'm not a jargon guy, but we're going to use it here. Mafic magmas are low silica magmas. Mafic magmas are created in pure oceanic settings. We can't have continental crust anywhere close. Mafic magmas are runny when they come out of the ground. All these things work together on the top line. You see it now. Let's keep going. If we take a hot spot and we go beneath a continent and we burn a hole in a continental crust, and we're miles from the ocean. This is the other end member. We have to be totally melting continental crust. We're going to create the highest possible silica with the highest possible viscosity. It's going to be stiff, sticky stuff. And that is felsic magma. I'm sure you're doing it, but just in case not, Yellowstone has felsic magma. Hawaii has mafic magma. And those words will be used a lot the rest of the quarter, and everything on the top row is associated with that word mafic, and everything on the bottom row, felsic. Morgan/Mason.
We were talking about feldspar earlier, and I recognized like the fel and felsic. Do they share a root for any?
They do, but let's not go there. But thank you. They do. There is a third choice. There is this 60% value, and let's just label that. I don't have enough room. Oh, why not? Intermediate. Not a very cool name, but let's use it. 60% magmas are intermediate magmas, halfway between the two end members. Now, we only have two types of crust on the planet, do we not? All we have got is continental crust and oceanic crust, and we can see what happens when we melt pure versions of those. So how and where are we going to find these intermediate magmas? Somebody we haven't heard from yet. Tony, we've heard from you. Go for it. Along the coasts. You remember 3 weeks ago, we had our magmas typically along the coasts. Well, why is it the coast, Mason?
Mason or Morgan? Because if the oceans are 45 and the continents are 70, 45 and 70 together are 60 if you average it out.
We're creating a hybrid. Hate that word these days, hybrid. We're creating a hybrid. We're creating a moderated version. Good job, Mason. We're mixing the mafic and the felsic together, and who's really on top of their game this morning? How is that possible plate tectonically? Love to get somebody else involved. How's this possible? How can we do this? How can we create this? How physically are we able to mix the, where does this happen? At the coasts, but like how? Casey. That's it. Good. Convergent, I'm giving you the plate boundary type if you don't have it. The type of plate boundary that generates intermediate magma at the coasts. Convergent, meaning the plates are coming together. Ocean crust, colliding with continental crust. Thicknesses are different, densities are different, we know all that. We send the ocean crust down the subduction zone. This is all according to Casey, and he's correct. When we first generate magmas deep in the crust, it's mafic. How much silica if it's mafic? Number, please. How much silica if it's mafic? 45. But the purpose of this diagram is to say when we actually have a volcano erupting lava at a coast, it's going to have intermediate magma. How much silica? Number? 60%. So why? Why did we go from 45% silica to 60% silica? I thought it was 45 down here. It is. It's 60 up here. Why? Hope? It's got to rise. And what happens as the magma rises? It starts as mafic. It starts to become less and less mafic, or it picks up silica as it rises. Why? JC? Yes, it's taking, remember the continent has 75% silica. Am I losing some of you now? Hope not. Continental crust has 75% silica. Oceanic crust has 45% silica. Now that we know this silica business, we've tied those things together now. Ocean crust, mafic. Continental crust, felsic. And what we're discussing right now, in case I'm losing you, we've only got a few minutes left, is how we are physically generating intermediate magma. And we're doing that by having our mafic magma begin truly as mafic magma, 45% silica, but as that mafic magma rises, I would visualize, at least I visualize, big chunks of continental crust falling kerplopping into this mafic magma batch and melting. We are assimilating big chunks of high silica continental crust in a very cartoonish way into that magma. And the point is, and JC sees it, and Hope sees it, and hopefully everybody sees it, as this magma rises through the continental crust, it gains silica. Again, by melting chunks of continental crust during its rise. And so yes, by the time it gets out, when Mount St. Helens erupts, or Mount Rainier erupts, or Mount Fujiyama erupts, or Kilimanjaro erupts, or Mount Popo above Mexico City, those are 60% intermediate magmas, but they weren't that originally. We finish with just a taste of what I was hoping we would do a lot of this morning. I've only got 3 minutes left. But that is to set up igneous rock classification. So I think I just want to play with you a little bit before we quit, and then we'll be a little bit more formal about this on Monday. Mafic magma, when it cools, is dark colored. Let's not even bother. Let's not even bother writing it out. But let me show you what mafic magma looks like when it comes out of a volcano. And it looks like this. So the mafic rocks are dark colored. They're made out of black minerals. This is a sample from Hawaii. These are samples from Hawaii that are younger than you are. Little babies. I'm crying, I'm a toddler. Stupid. There's all sorts of gases coming out with the erupting mafic magma. Now, if the mafic stays underground in the magma chamber, the rock is dark, but it has big, beautiful crystals in it. We'll save the rock names till Monday, although you'll learn the rock names in lab next week as well. Let's jump in the 2 minutes I have left to intermediate. Now we've left the oceans. I was just showing you ocean crust rock, by the way. Let's go to a coastal setting where we just did this hybrid story. Suddenly we leave rocks that look black from the oceans, and we truly get half and half. I mean, they visually look like a mixture of mafic and felsic. And if you're unaware, I guess you must be unaware at this point, the bigger the minerals, the more likely the magma cooled underground in a magma chamber. So these rocks, these igneous rocks that have these big minerals in them, formed in the dark in one of those magma chambers. What does it look like when that intermediate magma gets to the surface and erupts out of a volcano like this? So this is what andesite looks like. Audible yawn from Morgan now. Good. Now I'm calling you Morgan on purpose. Not happy with that autofocus on the oh, I guess that's you. That's you guys. I'm actually kind of pleased with it at home. You can see sparkly cleavage planes on occasion. Those are some of the minerals. But this is what andesite looks like. You remember the word andesite from a couple times ago. And then to finish out, what if we go to a true continental setting and we create some magma in a beer copper kettle in a truly continental setting? And the answer is beautiful light-colored rocks, even like, that's a bad example. Let me show you this one better. Okay? Hardly any black minerals now. So the continental crust creates these very light-colored igneous rocks. Lots of whites and grays and pinks. And so again, continental setting, this is what felsic magma looks like when it cools slowly underground. More audible yawning. They're loving the rocks now. They're lulling them to sleep. Lullaby, lullaby. Eat the chocolate left for you. Goodbye, goodbye.
Wow, Nick, that rocks.
Thank you, Morgan. Thank you to the Andersons for the gift. I'll make sure the late arrivals know about them, and I'll be back to talk and do a little live Q&A with you in just a second. Hey, did you come late? Lulu, I'll be with you in a second. Did you come late? Did you know about this gift for you now? Can somebody open the rest of these? Who's got it? These are gifts from home people by the name of the Andersons. Please, thank you. And you came on a Friday morning. You all did well in the quiz, so let's celebrate. If these get left, I'm going to eat them all. So you're going to take some for your parents, for your lovers. So please, I'm not suggesting it a little bit. I'm forcing you to eat chocolate. God dang.
I already know the grade. Yeah. You're right.
What the hell?
I'm glad you're struggling with
Bob, really?
Gotcha. I have all of the notes and everything else.
Thank you. Good to see you. Bye bye. Bye bye. Tim, bye. Oh, yeah. Yeah. Yeah, I'll have them again on Monday, but go for it. Yeah.
That's the one that have the big crystals for the Mafic.
Oh, the Gabbro. This is a Gabbro. Yeah. Yeah, it's pretty rare.
It's a phaneritic.
Correct.
Phaneritic.
Phaneritic, yes. Mafic that cools underground, bigger crystals, phaneritic texture. You did the 101 lab long ago, maybe.
No, this is just me studying. Just trying to
You never took 101.
Mm-mm.
That's why partly why you're here?
partly why I'm here. Just trying to catch up.
Huh.
Get everything on.
All right. Okay.
I did take 108.
Yeah.
Earth and energy resources.
Okay. Okay. Good. Young ladies. Oh, I'm sorry. Yeah. Here's my my office might be open, but in case it's not,
Okay.
and if you go in on the left is the stack of quizzes. You'll find them.
Okay.
Yep. Okay. Help yourself. Okay. I've got two grad students here. Some of you know, before I get to live Q&A, some of you know that there's a class of grad students who are practicing science communication, and they've asked if they can give a short talk to you guys as practice, and they're going to be graded on it as well. So we're not doing that today, but both Ben and Lulu are here, and I think, Ben, come on, let me answer a few questions, and let's just have you kind of screw around in the back and do what you need to do. And Lulu, you can kind of see as well. So both of these guys are grad students here, but they're also staff members. They're both instructors for the labs, and so they can be on camera since they're official employees. So let's do a little Q&A, and then I think Ben is going to talk to you on Monday. So on Monday, we will do volcanoes like normal. We'll do some live Q&A like normal. I might cut it short a little bit. And then Ben's going to have a 20-minute talk on Monday morning. We'll just keep the live stream going. And hopefully some of you will want to stick around and listen. And Ben's going to both these guys are going to do some live Q&A with you as well.
Have a great weekend.
Thank you, Morgan.
I was at a doctor's appointment.
You're good. You're good, man. Okay, thank you. You have a good weekend now. Okay, so they can be on camera. I've already said that, right? Okay. So why did the Eastern Washington fissures have a lower viscosity lava? Long story, Mr. Tony. We have 2 Columbia River basalt lectures, and let's save it for then. Does mafic equal basalt? I'm thinking runny magma and the German chocolate cake. Yeah, I don't know why I was so sluggish today, but I wanted to get to the igneous rock names, basalt, andesite, rhyolite, etc. And we'll have to do it quickly on Monday. But yes, if we cool magma quickly, if we cool mafic magma quickly above ground, we're going to get basalt. Is it clear? Okay.
Yeah, thank you.
Oh, you bet. Good. All right. Thank you, Eve. See you later. Thank you. How could there be basalt lava flows in Yellowstone Park? Michael, I'll give you a sneak peek. It's a bimodal volcanism system. So the Yellowstone hotspot not only creates the explosive caldera-forming felsic eruptions, but there's also mafic magma that comes as well. There's some models to explain that, but the data says that both ends of the silica spectrum are erupting from the same heat source. Maybe a surprise to you. You're right. The most recent eruptions in Yellowstone are basaltic, not the rhyolitic guys. Joseph, are there temperature differences across silicate magma types as well? Yes, the mafics are higher the magmas that are mafic in composition are higher temperature. And there's a whole set of ideas that I've long forgotten about Bowen's reaction series and different kinds of minerals crystallizing at different temperatures. It's quite an amazing set of discoveries by Norman Bowen, I think was his name, 100 years ago. But it's been a long time since I've been in an igneous petrology class, so I've lost that in my head. I can't even remember Mason's name, so how am I going to remember that? What does diorite look like? Ronnie, I think I tried to show it quickly. Yeah, you'll see these samples again on Monday, but these are the diorites. Are we happy with that autofocus, by the way? Like, is the autofocus effective with these samples? Okay, Ben, you want to try something out with these guys?
You're nervous. You have to.
Yeah, Lulu, you can just give it a try here. You're not really on microphone, so you can just kind of wave, and I don't know how much they'll hear you. So Ben is going to be talking on Monday. Ben's from Texas. Some of you met him early on, and he wanted to just see, I guess we want to problem solve and make sure that you can see his map. This is, yeah, put the chocolates down. Focus. All right. So yeah, I typically come this close. This is kind of a wide, so that, we can, it's kind of faint, but it depends on what are you thinking you want to talk about here?
I can't give up all the
Okay.
secrets. The magician, the river.
But you
the
want
river,
them to see the river. They
yeah,
can
the river's
obviously
the big thing. So
okay, and they can kind of see Saddle Mountains here. Okay, okay, good.
But another thing too, just
Yeah.
so you can hold the figure up. I want to see it.
This is Lulu. Lulu, where are you from?
I am from Spokane, Washington.
Lulu's from Spokane, in case you can't hear her. Yeah, you can.
Okay.
It always feels like you're way too close, but it's such a kind of a fisheye kind of a lens. And this will be right here so that you can keep one eye on it and kind of see how you're doing, if you're kind of off or on. But yeah, I mean, we can even bring the camera a little closer to you as well. But let's try it one more time, see if the autofocus kind of holds on that. If you come in and hold it pretty steady.
Yeah, it's showing
Yeah,
up pretty clear.
okay. All right, good. So you're Monday for sure, and you're thinking possibly Friday next week?
I wanted to present when you were talking about tsunamis, because that'd probably be it's my subject. So
Right.
I'd like to
Yeah.
then.
I think that's the following Monday, if I'm not mistaken.
Yeah, I think so.
Okay, so we might have 2 Monday talks, this coming Monday and the following Monday. That'll be our tentative plan. Okay. All right, anything else from you guys?
No.
Okay.
Thank you. Yeah.
Good, thank you, you bet. All right, guys. Okay, thanks for your patience. Let's do a little live Q&A with a few minutes left that we have. It's 11. I missed your, let me get down to live here. You might have to type in what you did again, I'm sorry. Papa Gino, I guess I'm just going to take my wireless mic and just clip it onto them real quick, I guess. I don't want to deal with another whole lab set. So we'll try to get it mic'd up properly. Is there a difference between silica content between and pahoehoe, or is it only temperature? Well, that's always confused me, though. These are different texture terms for basaltic lavas, most famously coming out of the ground in Hawaii. I don't really know. I can't remember. Has that really been figured out? Some of you know that pahoehoe is more kind of ropey chocolate frosting type textures, and is more blocky material. Those are Hawaiian words. Somebody I'm sure has the answer here. I don't know. Let me scroll back now in these most recent questions. I'm the singer for that theme song. is carbonatite a continental magma formed under special circumstances? Yes, but I don't remember anything. I've never seen a carbonatite, I don't think. I used to work with an igneous petrologist who really loved carbonatite, but I don't think I was listening when she was talking, or my eyes glazed over. I don't know. This is fun. Bunch of questions I don't know how to answer. Don, what is the makeup of red-colored volcanic rocks? Well, I assume you're talking about scoria, which is a mafic rock, so it's basaltic. Are you kind of talking about this kind of stuff that's pretty red, Don, and has a lot of holes in it? It's maybe more holes than it is solid, and you see it in landscaping if you're in Southern Cal or whatever. You know, those are cinders essentially. So the makeup is mafic magma, is this same kind of low silica magma we're talking about. But of course, there's other variables going on here about how much you can weather a mafic magma, what's the crystal size or what's the grain size of that igneous rock. Again, we'll do a little bit more about this with Monday. Tom, since I got to hold those rocks still a little longer for the autofocus. Yeah, that's a problem because, you know, I don't like to stand still. So you're right, but I may never have the autofocus really work properly because I'm not going to stand here for 5 seconds or more to get something to snap into focus. It's going to kill what I like doing. Calcite is not a silicate mineral. So not all minerals are silicates, meaning not all minerals are composed out of silicon and oxygen. So igneous rocks are almost all, or maybe they are all silicate minerals, but you know, there's calcite, there's halite, there's a lot of minerals that are not common rock forming minerals, and yet they are minerals for sure. See you, Ben. Thank you. Yeah, take more, please. What kind of magma comes from 75% viscosity? Well, first off, I just want to make sure we remember that number 75% was talking about the silica content, but I assume that's what you're talking about. The high silica magma has high viscosity, and so the lava domes that are in Yellowstone Park, for instance, or Big Southern Butte in southern Idaho, and there's plenty of high silica domes around the world. It's rhyolite, if that's what you're asking. Okay, we got Colin talking about what carbonatite is. It is nice when people are helpful to each other in here. It's also slightly annoying when we have people with no uncertainty about everything. And they just, yeah. It's great that everybody's here, but yeah. A few more. If you haven't picked up on it, magma chemistry is another weakness of mine. What are plutons, Alice? So a little sneak peek to Monday. When we fill these rooms underground, and of course they're not cartoonish like this, but if we fill that room underground with liquid magma, fine. And then we're going to have some eruptions with the volcano, great. And then eventually, when we remove the heat completely, we remove the heat source completely, whether that's a hot spot or a subduction zone or even a seafloor spreading center, if we change the tectonics and we remove the heat, we're going to solidify the entire underground magma chamber. And that's a pluton. So the pluton is just the term talking about a lot of underground magma that has cooled slowly. So you can have a pluton of granite, you can have a pluton of gabbro, etc. And if you have an extra big pluton, then that's a batholith. You know, again, I think you know enough about our world to know that there becomes this devotion to the terms. Like we're not even really talking about interesting ideas or concepts or explanation or field data. We're just out there talking about You said Pluton. What did you mean? I thought this was about. I thought it was a stock. I'm not picking on you, Alice. I'm just saying that it always, those kinds of discussions drive me crazy because I have no interest in arguing with somebody over what the right term is for something. I want to get to the mysteries and the interesting thoughts and the detective work and that stuff. Most of you know that about me already. Can I explain why the 2018 Kilauea eruption had higher than normal andesitic component? That's news to me if it did. Are you really saying there was an andesitic composition of some of the magmas at Kilauea? That surprises me if that's true. And if it is true, then I don't have an explanation. Lori, yeah, you can think of a Pluton as a place where a volcano used to be and it is no longer erupting, or it's gone, physically gone. You can also think of a Pluton as being a place where there was a lot of magma underground and the magma never did get to the surface. So you're not required to have a volcano with a Pluton, but usually Plutons are big enough that they feed some sort of vent up above. Charles, I did my best to shut you up yesterday, so I'm not even going to acknowledge you from this point forward, except to say I wish that you could join the group. And I wish you were able to pick up on the spirit of this group. We can't end on that. Let's do a few more. Kent's asking about serpentine, a hydrate of silica. Can it be black? Serpentine is a mineral that I usually associate with metamorphic rocks, Kent, so I wouldn't really associate it with these rocks unless I'm out to lunch. You know, there's a whole set of minerals that only form at very high temperatures and pressures, which means that really doesn't belong in this discussion. So I don't think I'll do more with serpentine because it's a metamorphic story as I remember it. Plus, I don't have much to say. I think of serpentine minerals as green more than I do black. What's that stuff that floats on water after erupting? Pumice, is that what you mean, Peter? So Lori, yeah, arguing between extinct and dormant. I just don't see the point. Thanks for the question, but I don't even know what the official definitions are, and I don't really care. Does water content affect the magmas as they're formed? Yes, and I'm ignoring that. So as usual, you see how I choose to teach things, and I focus on a couple of relationships and zero in on them. So you'll notice I was just focusing on differing silica content in these magmas. And if you are a magma expert, you know that it's way more than just silica content to explain these different volcanic styles. There are different volatiles, different gases in the magma system, which we'll talk a little bit about on Monday. There's different temperatures, there's different water content. So yes, there's many factors, but you know, working with non-science people, trying just to come up with a few relationships. I'm scrolling back. We'll do two more. I'm a little snarky here at the end. We don't want to end like that. We want to enjoy our weekend. So let me Lorraine says the earth is flat. Okay, well, that puts me in a better mood. Scrolling back for a couple of sane questions here. All right, we'll finish with this. The device 9 wants to know, curious to hear how you get mafic magma way inland. Yeah, well, that is the story with Eastern Washington. That's the story with Yellowstone. There's plenty of mafic magma in Yellowstone. And we're making progress in understanding magma systems. We're understanding mantle plumes a little bit better as we get better mantle tomography, for instance. But the short answer is possibly to say that if you get below the moho, it's mafic. If you get below the moho and you get into the mantle, which is beneath continental crust, Remember, I threw my chalk yesterday because they didn't have 70 kilometers thick ready to go for continental crust. So a 70 kilometer thick continental crust in the Rockies, let's say. But if we can somehow plumb deeper than 70 kilometers beneath Colorado, there's mantle material down there, which is mafic in composition. So it's really then a question of how can we split the continental crust? How can we rift the continental crust? How can we disrupt the continental crust sufficiently enough to get this stuff below the mantle to get up through the continent in a hurry and get that low silica magma to the surface? And if we can do that, and it has been done in places, then there you go. There you get mafic magma in the middle of a continental setting. Even the mid-continent rift. Back to that discussion once again. New Madrid, yeah. Yeah, the gabbros that I brought in, I only have a few gabbro samples, and I collected them from my grandmother Helen's backyard in Duluth, Minnesota. It's rare to find a gabbro. This is mafic magma that came up more than 1 billion years ago in the middle of the continent. Okay, I think that's enough. A toast to you. I really do appreciate you joining us for these. It's fun to have so many of you along. If nobody showed up, it just wouldn't be very fun. So here's to you for showing up regularly. Oh, I got to go get one of those chocolates. What a nice gift. There's only 3 left. I think these students are continuing to be surprised that you all are there, number one, and that you would actually take time to join us. So that in itself is a lesson. So you are role models, essentially. Autofocus. Hold it still. Autofocus. See, I'm just not that into this. It's still not snapping. Now it finally did. I got to cover up the whole screen with my hand. Oh, what? Here's to the health of your parents and your grandparents, your children and your grandchildren. Here's a special wish to those of you locked down and have been for weeks, and weeks coming in the future. Feels like there's no end in sight. I understand the stress of that. Hang in there. And here's to sunny skies and warmer weather for those of us, at least in the Northern Hemisphere. Thanks for joining us today. Have a good weekend. I'll see you on Monday, 10 o'clock, lecture, a little bit of live Q&A, and then Ben from Texas, using his map and his mouth, and be ready to enjoy his 20-minute talk and about 10 minutes of live Q&A, and his professors will be grading him on his performance. Thank you. I love you. And end stream, goodbye, goodbye, goodbye. That's good chocolate.